a quiet beginning. What if you were told that right now, somewhere in the absolute silence of space, there is a place where yesterday and tomorrow have swapped positions? A place where time doesn't just slow down. It physically bends into a destination you can walk toward. You don't need a ship. You don't need a heavy suit pressing against your shoulders or the mechanical hum of life support in your ears. Imagine simply being there, suspended, weightless, resting in the cool, infinite dark. Around you, the universe is ablaze with quiet beauty. Billions of ancient suns burn with steady, unfiltered light against a backdrop of deep obsidian. The Milky Way arcs across your field of view like a pale silver ribbon, its glowing dust clouds floating frozen in time. Everything out here feels permanent, reassuring, and completely still, until your eyes catch a subtle flaw in the starfield. Far out in the distance, something is quietly wrong with the night sky. It isn't a blazing firestorm. It doesn't roar, flash, or hurl cosmic debris. It rests in the sea of stars as a smooth, perfectly spherical shadow, a circle of absolute darkness that seems to absorb the surrounding void. Look closer at its edges. The stars positioned directly behind this dark sphere aren't just hidden. Their light is behaving in ways that defy everything you know about straight lines. Starlight passing near the perimeter is being drawn outward, stretched into long, shimmering arcs of pale gold and liquid blue. It is as if an invisible, flawless magnifying glass of impossible scale is hovering in deep space, slowly warping reality around its frame. You are looking at a black hole. From this distance, there is no violence. Gravity here is gentle, predictable, and calm. You can float weightlessly, watching this shadow bend the universe without a single trace of fear. For decades, popular myths have painted black holes as ravenous cosmic vacuum cleaners, wandering through galaxies and indiscriminately pulling in entire solar systems. They don't. If our sun were replaced this very second by a black hole of the exact same mass, the Earth would not be yanked into a dark vortex. We wouldn't plummet into an abyss. Our planet would simply continue moving in its quiet, cold orbit, completely indifferent to the loss of light. Gravity doesn't magically multiply simply because an object collapses. A black hole is not a hollow void or a tear ripped through the fabric of space. It is a region where an immense amount of mass has been compressed into an impossibly small volume. When that much weight is crowded into so little space, gravity ceases to be just one force among many. It becomes the only force that matters. It curves the geometry of space-time so steeply that light itself can no longer travel straight outward. That is why it appears dark. The object isn't hiding. Its gravity has simply turned all outgoing paths of light inward, casting a pure gravitational shadow against the starry cosmos. As you glide a little closer, the dark circle slowly expands in your field of view. It remains completely motionless. The void around it stays silent. Yet the constellation patterns framing the shadow are beginning to twist into surreal, fluid shapes. Astronomers call the outer border of this dark sphere the event horizon. Think of it not as a physical barrier, but as a quiet threshold in space. You won't bump into a hard surface. You won't feel a thud or a sudden jolt. If you fire your engines while resting outside this invisible line, you can turn around and navigate safely back into the open cosmos. Outside the threshold, space offers choices. You can move forward, backward, left or right. Cross it, however, and the fundamental rules of geometry shift. Inside that boundary, the curvature of space becomes so extreme that every forward-directed path points toward the center. Every direction you could possibly face leads inward. The spatial path toward the core takes on the relentless, inescapable nature of time itself. At the very center of that region, classical mathematics predicts a singularity, a point where all that stellar mass is compressed into zero volume, yielding infinite density. Physicists know that infinity is rarely a physical reality. It is simply a signpost telling us that our current equations have reached their boundary, waiting for a deeper quantum understanding of gravity to explain what truly sits at the core. Long before anyone could capture an image of a black hole, thinkers wondered if a star could ever grow dense enough to trap its own light. During the First World War, when Karl Schwarzschild solved the mathematical equations for a collapsed mass from the trenches of the Russian front, even Albert Einstein assumed nature would always prevent such extreme objects from actually existing. Yet here, it rests before you. A silent, unhurried monument to a colossal star that burned through its life, ran out of nuclear fuel, and collapsed until no known force in the universe could stop the fall. The shadow hangs ahead of you, dark, calm, and patient. You aren't plummeting violently. You aren't being torn apart. You are simply drifting, weightless, carried by the natural, unforced geometry of space-time. As you move nearer to the edge, the distant starlight behind the shadow stretches further, curling into delicate, glowing rings of light. The night sky ahead begins to fold inward, and the quiet darkness slowly opens up to receive you. Let's step into the shadow, meeting the monster. As you drift slowly through the dark, the black sphere in front of you remains steady and calm. It does not move, it does not pulse, it simply rests there, a quiet circle of absolute night drawn against the distant field of stars. From where you float, it is easy to think of this shadow as something that has always been here. It feels ancient, permanent, and unmoving, as if it were a fundamental feature of the universe that existed long before the stars themselves were lit. Every black hole has a story. Every single shadow hanging in the deep void was born from something that came before it. To understand what you are floating toward, you have to turn back the hands of the cosmic clock. You have to travel back through millions of years to a time when this exact coordinate in space was not empty at all. Long ago, there was no shadow here. There was only light, heat, and unimaginable scale. In place of this silent dark, a colossal star once burned. It was a stellar titan, a blue supergiant, tens of times more massive than our sun, and hundreds of thousands of times brighter. It blazed with a fierce, brilliant energy, casting a pale indigo light for light years across the surrounding gas clouds. If you had stood at this exact distance back then, the star would have filled your sky with a searing, roaring brilliance. A star like that lives its life in a state of delicate, continuous tension. It is a lifelong struggle between two immense forces that never rest. On one side is gravity. The sheer weight of the star's massive body is constantly trying to pull every atom inward, trying to crush the star down into the tightest possible ball. Gravity is patient, heavy, and endless. On the other side, fighting back against that weight, is the heat of nuclear fusion. Deep inside the star's central core, where the pressure is unimaginable, hydrogen atoms are crushed together until they fuse into helium. Every time two atoms join, they release a tiny burst of energy. Multiply that by countless trillions of reactions happening every second of every day, and you get an outward pressure, a continuous radiant wind pushing outward from the center, holding the weight of the star up against its own gravity. For millions of years, these two forces hold each other in check. Gravity pushes down, fusion pushes up. The star stays stable, shining brightly into the quiet void. It is a balance so perfect that it seems as if it could last forever. A star that burns so brightly burns through its life at a terrifying speed. Smaller stars like our sun can pace themselves, burning quietly for billions of years. A supergiant, however, consumes its fuel with extravagant haste. In a few short million years, the core runs out of hydrogen. When the hydrogen is gone, the outward pressure vanishes. For a brief moment, gravity wins. It crushes the core tighter and tighter, spiking the temperature inside until it grows hot enough to ignite the leftover helium. The core begins fusing helium into carbon, and the outward pressure returns, holding gravity back once again. This becomes the star's pattern in its twilight years. It burns through hydrogen, then helium, then carbon, neon, and oxygen. Each stage lasts a shorter time than the one before it. The star becomes like an onion, layered with different elements, fighting a desperate, losing battle against its own relentless weight. When lighter elements fuse, they release energy, providing that crucial outward push. But iron does not release energy when it fuses. Iron absorbs it. The moment the star's core turns to iron, the nuclear engine inside dies. There is no more heat. There is no more outward pressure. The core goes cold in an instant. After millions of years of perfect balance, the support holding up the star simply disappears. What happens next takes less than a second. Without the outward push of fusion, gravity takes complete control. The entire outer body of the star, billions upon trillions of tons of gas, comes crashing down toward the core at a significant fraction of the speed of light. The core is crushed down so violently that its atoms are demolished, squeezed into a solid, impenetrable ball of pure neutrons. The collapsing outer layers hit that dense neutron core and bounce back with catastrophic force. The result is a supernova, one of the most energetic events in the entire universe. The outer shell of the star is blasted into deep space in a blinding wave of light, heat, and newly forged heavy elements. For a few weeks, this single dying star glows bright enough to outshine an entire galaxy of 100 billion suns. When the glowing debris of that explosion slowly expands away over thousands of years, floating out to seed future planets and future worlds, what is left behind at the center? The core remains. Because the original star was so massive, the weight resting on that neutron core was too great for any known force in nature to resist. The collapse doesn't stop. The neutrons themselves give way. The core continues to fall inward on itself, shrinking past the size of a planet, past the size of a city, past the size of a single atom. It keeps falling, squeezing all of that star's remaining weight into a space smaller than anything human eyes could ever measure. It drops out of sight. It leaves behind only its weight, a concentrated knot of gravity warping the space around it. The event horizon forms like a dark veil drawn over the place where the star used to be. That is how the black hole in front of you was born. It is a stellar mass black hole, the cold, quiet ghost of a colossal star that burned out its life eons ago. As you float here, looking at this dark remnant, it is worth knowing that the cosmos holds black holes of vastly different scales. The shadow ahead of you is only a few dozen miles wide. It carries the weight of perhaps 10 or 20 suns. Throughout our Milky Way, there are millions of stellar black holes just like this one, resting quietly in the spaces between the stars. If you were to travel to the very center of our galaxy, however, you would find a very different kind of object. At the core of the Milky Way sits a supermassive black hole, a giant containing the mass of 4 million suns. Its dark horizon stretches for tens of millions of miles across space. Out in the wider universe, in the hearts of distant galaxies, there are monsters with the weight of billions of suns, casting shadows larger than our entire solar system. Scientists are still trying to understand how those supermassive giants grew so large so early in the history of time. Some may have started as stellar black holes that consumed gas and merged with others for billions of years. Others may have formed directly from the collapse of vast ancient gas clouds in the young universe. Big or small, their fundamental nature is identical. They are places where mass has overcome every other force, leaving behind a shadow that bends the light of the universe around it. You look back at the black circle in front of you. It sits quietly in the dark, indifferent to the violent story of its birth. The brilliant blue star is gone. The blinding supernova has faded into history. Only the silent curvature of space remains. You are floating a little closer now. The background stars are stretching further, curving around the black perimeter like glowing ribbons of glass. The dark sphere seems to grow larger in your view, not because it is moving, but because your path is gently carrying you inward. The night sky behind you is beginning to twist. Space itself is beginning to shape how you see the world outside. Let's watch as the light begins to warp. The first strange thing. As you move closer to the silent black sphere, the first thing you notice isn't a feeling of pull or a sudden rush of speed. It is a quiet, optical transformation of the universe around you. Up until this moment, the stars in the deep background looked normal, steady points of light set against a dark canvas. But now, as the distance between you and the shadow shrinks, the night sky begins to bend in ways that feel entirely unnatural. The black circle in front of you is no longer just blocking the stars behind it. It is rewriting where those stars appear to be. Directly around the rim of the dark sphere, the starlight is being drawn outward and curved around the edge. Stars that should be hidden directly behind the black hole aren't hidden at all. Their light travels through space, passes near the edge of the shadow, and gets pulled around the curve toward your eyes. You are seeing stars that are actually located straight behind the black hole, appearing instead as blowing, stretched arcs around its perimeter. This is gravitational lensing. For centuries, we were taught to think of light as something that travels in perfectly straight lines. A beam of light shines from a star, passes through the vacuum, and arrives at an observer in an unbroken path. But light doesn't travel along rigid geometric lines. It travels through space-time, and space-time is flexible. When a massive object rests in space, its weight creates a gentle depression in the fabric around it. When light passes near that depression, it simply follows the natural contour of the curved space. It isn't that the light itself is being yanked by a physical force. The path the light must follow has simply been bent. Because the black hole packs so much mass into such a small region, the curvature of space around it is extraordinarily steep. As you glide closer, watching the stars distort, you see a bright star near the edge of the shadow appear to split. One image of the star sits just outside the upper curve of the dark circle. The second image of the exact same star appears near the bottom curve, stretched into a thin thread of light. As you move slightly, the two images slide around the perimeter of the shadow, joining together to form a glowing ring of light that completely circles the black sphere. This circle of light is what astronomers call an Einstein ring. It happens when a distant light source, the black hole, and your eyes line up in near-perfect alignment. The light from that single distant star is bent equally in every direction around the dark horizon, wrapping the shadow in a delicate ring of starlight. You watch this ring for a long time. It hovers motionless in the dark. For a while, you simply watch. The stars continue bending. The shadow grows. Nothing else happens. Yet somehow, everything looks different. As you draw closer, the distortion grows more pronounced. The sky behind you is beginning to look as though it is being viewed through a glass lens. Stars near the edge of the black sphere move faster across your field of view than stars further away. Constellations you have known your whole life are stretched out of shape, their familiar patterns warped into long, curved swoops of pale light. Yet, despite all this strange motion in the sky, everything around you feels perfectly still. You aren't shaking. There is no sound. There is no wind brushing past you. You are in free fall, moving weightlessly through space that is quietly bending around you. Near the inner edge of this distorted field of light, right where the dark shadow meets the warped starlight, you notice a subtle feature. A thin ribbon of light sits just outside the shadow. That subtle ring is near the photon sphere, a region located at about 1.5 times the Schwarzschild radius. To understand what you are looking at, consider that light doesn't just pass by a black hole and get deflected. At this specific region, gravity is strong enough that photons approaching at just the right angle can briefly orbit the black hole before escaping outward or falling inward. What you see in that thin glowing area is strongly lensed light, including photons that have wrapped around the curvature of space before reaching your eyes. In theory, if an observer could somehow remain stationary right at this orbital threshold, light reflecting off the back of their own head would travel around the black hole, allowing them to see their own reflection stretched along the horizon in front of them. In reality, these photon paths are extremely unstable. The slightest nudge sends light falling inward or escaping out into space. But from where you glide, watching from a safe distance, it looks like a glowing border separating the warped light of the universe from the darkness ahead. The black circle is much larger now. As more and more of the forward sky is occupied by the growing shadow, the light from the rest of the universe is being gathered into a shrinking bowl of stars behind you. Much of the sky ahead is turning dark. The starlight gathering behind you appears increasingly blue-shifted as the light falling in behind you gains energy. You continue past the photon sphere now. The thin ring of orbiting light fades behind you. The distorted arcs of distant stars are squeezed toward the edges of your vision. In front of you, the smooth surface of the event horizon grows closer with every passing moment. The horizon is closer now than ever before, and nothing beyond it has ever returned to tell the story. Falling begins. Crossing the point of no return. The region of the photon sphere now rests behind you. As you continue forward, the motion is so smooth that if you closed your eyes, you would feel completely stationary. There is no sensation of speed, no wind, no vibration against your body. You are simply following a natural contour of space-time, gliding weightlessly toward the dark silhouette ahead. For a long while, you simply watch. The background stars continue their quiet, distorted dance. The shadow in front of you grows larger, taking up more and more of your field of view. Nothing else happens. The void remains completely silent. Yet somehow, everything looks subtly different from how it did just a few moments ago. The sky behind you is beginning to compress. Because space-time is curved so sharply near the edge of the black hole, the starlight entering from the rest of the universe is being gathered into a shrinking circle of light straight behind you. It almost feels as though you're looking back out at the cosmos through the open end of a glowing tunnel. The starlight in that shrinking circle appears increasingly blue-shifted as the light falling in behind you gains energy along the steep gravitational slope. Meanwhile, ahead of you, much of the view is occupied by the dark horizon. It is important to understand what is happening to your perception of time and speed as you approach this boundary. If a friend were watching you from a safe distance far away using a powerful telescope, they would see something extraordinary. As you get closer to the invisible edge, the light bouncing off you would take longer to climb out of the deep curvature of space-time. To your friend, your forward movement would appear to slow down. As you reached the boundary, your distant friend would see your image freeze. You would appear suspended in time, hovering at the threshold, while the light reflecting off you faded into deeper reds, infrared, and eventually invisibility. To the outside universe, you would never actually be seen crossing the line. But that is only how it appears from far away. Your own experience is completely different. In your local frame of reference, time moves normally. Your watch ticks at its usual steady rhythm. Your heartbeat remains calm. You do not freeze, nor do you slow down. You glide straight past the point where the outside world sees you stop. You are now only moments away from the threshold itself. Many people imagine the event horizon as a visible surface, a dark, shimmering film stretched across space, or a hard wall where reality abruptly breaks. It is neither. The event horizon has no physical wall. It is a mathematical threshold in space. Time, simply the region where all future directed paths through space curve inward toward the center. If you were falling with your eyes closed, you would feel nothing unusual as you passed through it. There is no bump, no physical resistance, no sudden flash of light to mark the moment. The darkness ahead fills more and more of your view. The circle of starlight behind you has gathered into a luminous disk, framing the dark horizon like a crown of light. The starlight from distant galaxies and ancient suns is gathered there, shining down on you from the universe you are leaving behind. Then, almost imperceptibly, you pass the invisible boundary. You have crossed the event horizon. Outside, the universe continues its ancient, unhurried march. Stars burn out, galaxies rotate, and billions of years roll past. But for you, the path backward has quietly closed. Inside the horizon, the curvature of space becomes so extreme that the roles of space and time undergo a strange conceptual shift. Outside, you had complete freedom to move forward, backward, left, or right in space, while time carried you relentlessly into the future. Now, inside the horizon, moving inward toward the center, behaves like time itself. Moving inward is no longer a choice of direction in space. It becomes your future. Just as you cannot step backward into yesterday, you cannot turn around and move outward toward the edge. Every possible path, every beam of light, and every tick of your watch points inevitably toward what lies ahead. Yet, as you look around in this new realm, there is no immediate chaos. The light that crossed the horizon alongside you and behind you continues to reach your eyes. The bright window looking back at the outside universe remains visible behind you, shining quietly in the dark. You are falling, weightless and calm, through a region of space where no human eye has ever looked, carrying the quiet light of the cosmos with you into the deep unknown. The horizon rests behind you now, and nothing that has ever crossed this line has ever returned to tell the story. Time starts breaking. As you fall further beyond the event horizon, a deep, eerie quiet settles over your senses. The weightlessness remains absolute. There is no wind tugging at your clothes, no roaring engine, no sudden pull in your chest. You are simply moving along the curved geometry of space-time, drifting silently into the dark. Yet, as you gaze back at the bright disk of starlight frame behind you, a realization begins to take shape. Time itself is no longer behaving the way you have known it your entire life. To understand what is happening around you now, we have to look back at one of Albert Einstein's most remarkable insights. Time is not a universal, steady clock, ticking away at the exact same rate for everyone across the cosmos. It is flexible, woven directly into the fabric of space. The deeper you sit inside a gravitational well, the slower time ticks relative to someone standing further out in flatter, calmer space. This is gravitational time dilation. It is not an illusion, nor is it a trick played on our mechanical clocks. It is a fundamental truth of reality. Even on Earth, time ticks ever so slightly slower at sea level than it does on the peak of a high mountain, simply because sea level is closer to the center of Earth's mass. The difference is measured in fractions of a nanosecond, far too small for human senses to feel, but precise enough that our satellites and global positioning systems must account for it every single day. Here, deep inside the gravitational well of a black hole, that subtle difference stretches into something extraordinary. Looking back through the glowing circular window behind you, the starlight from the outer universe is not just bright. It is changing rhythm. In popular science, people often imagine that falling into a black hole means you will watch the entire future of the universe play out before your eyes, like a film on fast forward. The reality, as physicists know, is far more complex. What you can observe depends entirely on your exact trajectory. The type of black hole you have entered, and the finite amount of time you have before reaching the center. Yet, as incoming light rays gather from the cosmos behind you, the starlight reaching your eyes can appear compressed in time, because time for you is ticking at its own steady local pace, while time in the outside world runs at a vastly different rate relative to your position. The incoming light arrives carrying information from the outer cosmos at an accelerated pace. You watch as the light from background stars shifts in subtle, unexpected ways. Distant cosmic events, processes that play out over long spans of time in deep space, send their photons down into the well, reaching your eyes in condensed succession. Yet inside your own frame of reference, nothing feels rushed. Your pulse remains calm and slow. If you look down at your watch, the second hand ticks forward with familiar, unhurried precision. 1 second still feels like 1 second. A single breath takes the exact same time it always has. This is the strange beauty of relativity. Time always feels completely normal to the person experiencing it. It is only when you compare your clock to a clock resting in a different part of space-time that the rift becomes visible. The universe behind you is aging, moving through time on its own path, while you carry your own local present moment with you into the dark. To truly appreciate how profound this shift is, consider what happens when we compare two observers moving through different regions of gravity. Imagine leaving an atomic clock far out in deep space, millions of miles away from any planet, star, or black hole. That clock rests in a region of flat space-time, where gravity is virtually non-existent. It ticks at a steady baseline rate, serving as the cosmic standard for calm space. Now imagine carrying a second, identical atomic clock with you as you drift down into the black hole. At first, when you are far away, both clocks tick in near perfect synchronization. Every second registered by the clock in deep space corresponds to a second registered by the clock in your hands. But as your path carries you deeper into the gravitational curve, the tick of your clock begins to diverge from the tick of the clock left behind. As you approach the event horizon, the gap between the two clocks widens at an accelerating pace. To an observer standing beside the clock in deep space, looking at your clock through a powerful telescope, the second hand on your clock appears to slow down. Each tick takes longer than the last. As you reach the boundary of the horizon, the distant observer sees your clock's second hand freeze entirely. To them, your time has come to a complete standstill. Yet to you, holding the clock in your own hands, there is no slowing down. You look at the second hand, and it clicks forward smoothly, once every second, without a moment of hesitation. If you look out through your viewing window toward the clock in deep space, you see the opposite effect. The second hand on the distant clock is spinning rapidly, whirring around its face like the blades of a fan. Minutes pass in seconds, hours pass in minutes, years pass in hours. You are standing in a region where the fabric of time has been stretched thin by mass. allowing you to watch the light from the outside universe stream down into the dark, while your own personal time remains steady, quiet, and unbroken. As you continue inward, the light from the outside universe gathered in that circular window grows increasingly concentrated. The window itself appears to shrink in size, squeezed by the extreme curvature of space around you, but the light pouring through it becomes sharper and more intense. The starlight is shifted into higher energies, moving toward cooler, brighter blue tones and into invisible, ultraviolet wavelengths. The window looks like a glowing eye staring down at you from the universe you left behind, casting a cool, pale light across the darkness. For a long while, you simply float and observe. There is no need to measure the passage of time anymore. The concepts of minutes, hours, and days belong to worlds with rising suns and turning horizons. Here, there is only the present moment, weightless and serene, suspended inside a quiet cascade of ancient starlight. You watch as the incoming light from distant star clusters shifts softly in the dark sky above. Nebulae and distant galactic structures send their pale beams down into the deep well. To your eyes, it unfolds like a quiet evening sky turning from dusk to night. You are witnessing the deep mechanics of time, carrying your own quiet present through the dark. And as the glowing window behind you slowly shrinks, becoming a brilliant point of diamond light set against the dark, you turn your attention back to the space surrounding you. The familiar rules of geometry are beginning to bend out of shape, preparing to show you a world where space itself stops behaving. Space stops behaving. In our ordinary lives on Earth, space feels predictable, reassuring, and firm. We learn from an early age that a straight line is the shortest distance between 2 points. If you walk straight ahead without turning, you move in a flat, predictable direction. Parallel lines stay parallel forever, never crossing, never drifting apart, maintaining their quiet separation across any distance you choose to walk. We build our cities, our homes, and our maps on this simple foundation. It feels like an absolute truth, woven into the very air we breathe. But flat space is a luxury of regions far removed from heavy masses. Here, deep inside the black hole, space stops behaving according to those simple, everyday rules. Space-time is curved. To visualize what this means, imagine an ant crawling across the surface of an immense, perfectly smooth glass sphere. To the ant, walking forward feels like traveling in a straight line. It doesn't feel itself turning left or right, it simply steps forward, one small foot after another, following what feels like a flat path. Yet, because the surface it walks upon is rounded, its path naturally curves around the sphere. If 2 ants start at the equator of the sphere, walking due north parallel to one another, they will eventually meet at the North Pole. They didn't turn toward each other. They didn't alter their steps. The very shape of the surface beneath them drew their paths together. In physics, these natural, unforced paths through curved space-time are called geodesics. When you fall through a black hole, you are not being yanked by an invisible rope. In Einstein's theory of general relativity, gravity is best understood as the geometry of space-time itself. You are simply following a geodesic, a straight path through a space that has been profoundly, steeply curved by mass. Because space is so intensely curved here, straight lines in the ordinary Euclidean sense no longer exist. If you were to shine a beam of light straight out to your side, expecting it to travel away in a flat, infinite line, you would be surprised by what happens. The curved geometry of space-time bends the light's path inward, sweeping it around toward the center alongside you. Every possible trajectory for matter, light, and energy is drawn along paths that lead deeper inward. Even your perception of distance and direction begins to warp in ways that defy everyday intuition. If you tried to measure the distance between 2 points inside this region using a rigid ruler, you would find that spatial dimensions no longer hold their familiar proportions. The space ahead of you appears stretched out toward the center, while the space around your perimeter feels compressed. It is as though the invisible room you are floating in is being gently reshaped, not by pushing against your physical body, but by altering the very coordinate grid upon which reality is drawn. Yet, despite this strange geometric bending, there is no physical noise, no turbulence, and no sudden jolt. The curvature of space-time is smooth, continuous, and quiet. It is a graceful restructuring of direction and distance, carrying you softly forward along its natural contours. You are moving through a realm where space and time have merged into a single, flowing geometry. Consider what happens to the concept of spatial freedom inside this curved landscape. In the world outside the horizon, space provides you with 3 dimensions of movement. You can move up or down, left or right, forward or backward. If you walk into a room, you can choose to stand still, turn around, or walk back out the door you came through. Space offers options. Time is the only dimension that flows strictly in one direction, carrying you relentlessly from yesterday into tomorrow. Inside the horizon, those roles have undergone a profound, fundamental swap. The radial dimension, the spatial path leading toward the center, now acts like time. Just as you cannot stop yourself from aging, just as you cannot pause the steady march of seconds into minutes, you cannot stop your forward movement along this radial coordinate. Moving inward is no longer a spatial journey you choose to make. It is your temporal future. The center of the black hole is no longer a location sitting in space ahead of you, like a destination on a map. It has become a moment in time waiting in your future. To try to avoid the center by firing rockets or turning sideways would be like trying to avoid next Tuesday. It is an impossible concept because the geometry of space-time itself has woven that future into the fabric of your path. Yet, as strange and surreal as this geometric reality is, the immediate space around your body remains calm and peaceful. You look back one more time at the shrinking window of starlight behind you. It is smaller now, a bright, luminous point resting in the dark sky above, shining like a lonely diamond at the top of a deep, dark well. The outside universe is still out there, ancient and vast, but its light is now just a distant memory guiding your way through the unknown. For a long, quiet moment, you simply drift in the stillness. There is no wind. There is no sound. There is only the dark, smooth expanse of space bending quietly around you, holding you in its weightless embrace. The universe behind you continues its vast, ancient story, while you float peacefully along your geodesic path, deeper into the heart of the shadow. Ahead of you, the path continues inward, smooth and unbroken, leading toward a neighborhood where the environment grows vastly more intense. Take a deep, slow breath. The dangerous neighborhood. Up until now, our journey has been an exercise in pure geometry. We have watched light bend, space stretch, and time alter its pace, all in a realm of tranquil silence. But if you were to approach a real black hole out in the wild universe, you would quickly discover that the space surrounding it is rarely clean, empty, or quiet. Before you ever reach the event horizon, you must pass through its neighborhood, and in many cases, it is the neighborhood, not the black hole itself, that poses the most immediate danger. Most black holes do not sit in absolute isolation. They drift through galaxies filled with interstellar gas, dust, and nearby stars. Because a black hole concentrates so much mass into such a small volume, any stray gas or matter that wanders too close gets caught in its deep gravitational well. As this material falls inward, it rarely falls straight down. Just as water swirling toward a drain spins faster and faster, incoming gas begins to orbit the black hole, flattening out into a massive, rotating structure known as an accretion disk. Imagine a glowing, razor-thin plate of superheated gas spanning millions of miles across, spinning around the dark central horizon at a significant fraction of the speed of light. Inside this accretion disk, matter is subjected to extreme friction and gravitational squeezing. Gas near the inner edge orbits much faster than gas further out, creating intense shear forces. Atoms slam into one another at thousands of miles per second, converting gravitational energy into raw heat. The temperature of the disk climbs from thousands of degrees to millions, glowing brightly across the spectrum from visible light to intense ultraviolet rays and scorching X-rays. For an observer approaching from deep space, this disk is often the very first thing you see. It wraps around the dark silhouette like a ring of liquid fire. Its brilliant light distorted by the same gravitational lensing we explored earlier. Light from the far side of the disk is pulled over the top and under the bottom of the black hole, making the disk appear to wrap completely around the central shadow in a surreal, glowing halo. Yet, as blinding and intense as the accretion disk appears, the environment gets even more dramatic. Swirling within this superheated plasma are immense magnetic fields. As the charged gas rotates around the black hole, it drags the magnetic field lines along with it, twisting them into tight, coiling spirals above and below the poles. When these magnetic fields get squeezed to their absolute limits, they act like particle accelerators on a cosmic scale. A portion of the matter falling toward the black hole is caught in these magnetic funnels before it can cross the event horizon. It is redirected outward, blasted away from the poles in two narrow, ultra-dense beams of plasma known as relativistic jets. These jets shoot out across thousands of light-years into deep space, beaming high-energy radiation across entire galaxies. If you are falling toward a black hole with an active accretion disk and powerful jets, the radiation alone would be fatal long before you ever touch the horizon. The X-rays and gamma rays pouring from the disk would sanitize any spacecraft, making a peaceful descent impossible. This is why, for our journey, we chose a quiet, isolated stellar mass black hole, one that has swept its surroundings clean of stray gas and dust. Yet, even in a clean, quiet system, the dangerous neighborhood leaves its mark on the space around you. The invisible lines of gravity are still there, waiting patiently as you glide inward, preparing to show you what happens when gravity stops pulling on your body as a whole and begins pulling on your individual atoms. Take a slow, deep breath. Spaghettification. Have you ever wondered at what precise moment the human body notices the true shape of gravity? In our daily lives on Earth, we experience gravity as a uniform, comforting pull. When you stand on the ground, your feet and your head feel essentially the same downward force. You don't feel as though your toes are being yanked while your shoulders float weightlessly. That is because the Earth is vast, and the distance from your head to your feet is tiny compared to the 4,000-mile radius of the planet beneath you. The difference in gravitational pull between your top and your bottom is practically zero. But near a black hole, that comfortable uniformity disappears. Because a black hole packs an immense amount of mass into an extremely small space, the strength of its gravity changes dramatically over very short distances. This variation in gravitational force across the length of an object is what physicists call a tidal force. To understand tidal forces, think of the Moon and the Earth's oceans. The Moon's gravity pulls slightly harder on the side of the Earth closest to it than it does on the center of the Earth, and harder on the center than on the far side. This tiny difference stretches the Earth's oceans into a subtle oval, creating the tides that rise and fall along our shorelines every single day. Now, imagine taking that same stretching mechanism and multiplying its strength by trillions. As you fall feet first toward a stellar mass black hole, Your feet are closer to the center of mass than your head. In flat space, a few feet of distance means nothing. But here, where space curves sharply over a distance of inches, your feet experience a significantly stronger pull than your head. At first, the difference is gentle, a faint, imperceptible tension running through your body as if you were stretching after a long sleep. As you draw closer, that tension grows. Your feet are pulled downward faster than your head, while simultaneously, the curved paths of space draw your shoulders inward toward the center, squeezing you from the sides. You are being stretched vertically along your line of fall and compressed horizontally across your width. Astrophysicists give this remarkable phenomenon a surprisingly literal name: spaghettification. It is the process by which any object, whether a spacecraft, an asteroid, or an astronaut, is stretched into a long, thin, thread-like shape as it approaches a small, dense gravitational source. Here lies one of the most surprising paradoxes in black hole physics. The smaller the black hole, the more violent the spaghettification outside its horizon. For a stellar mass black hole like the one we have been observing, the event horizon is small, only a few dozen miles across. Because the horizon is so close to the central concentration of mass, the tidal forces outside the horizon are immense. For a human falling into a stellar mass black hole, spaghettification would tear you apart long before your feet ever cross the event horizon. In contrast, if you were to fall into a supermassive black hole, a giant containing billions of times the mass of our Sun, the story is entirely different. Because a supermassive black hole is so enormous, its event horizon stretches across billions of miles. When you approach its border, you are still millions of miles away from the central mass. The gravitational slope across the length of your body is extremely gentle. If you fell into a supermassive black hole, you would cross the event horizon without feeling any stretching at all. You could glide right past the point of no return, weightless, calm, and unharmed, enjoying the view of the universe behind you while floating inside the dark. Spaghettification would only catch up with you much later, deep inside the horizon, as you finally approach the central core. As we drift through this quiet region of our journey, we remain in a realm of pure thought, observing these forces from a safe, weightless vantage point. You watch as stray particles in space ahead of you align themselves along the steep lines of curved space-time, drawn into long, slender trajectories pointing straight inward. The very grid of space is showing you its stretch, quietly demonstrating how gravity transforms matter when pushed to its ultimate limits. There is no pain, no tension in your own frame. You are simply observing the grand scale of the cosmos, where the laws of nature shape atoms and stars with the same unhurried precision. The dark void surrounds you now, calm and deep. The dangerous neighborhood and the stretching tides have revealed their secrets. Ahead of us lies the threshold where science shifts from what we can observe to what we can only calculate. Take a slow, deep breath inside the event horizon. Silence, not just the absence of sound, but a quiet so profound that it feels woven into the darkness itself. You are inside. If you close your eyes, nothing has changed. Your breath is slow and steady. Your heart beats with the same calm, familiar rhythm. You do not feel a wall behind you. You do not feel a floor beneath your feet. There was no physical barrier to mark the crossing, no surface to shatter, no sudden jolt, no flash of light to signal that you had stepped beyond the edge of the known universe. Yet, when you open your eyes, the void around you reveals a truth that no human eye was ever meant to see. Looking backward, the universe you left behind has pulled back into a single, luminous window hovering in the dark sky above. It shines like a brilliant, solitary jewel set into a vault of pure obsidian. The starlight, entering through that circular portal, is gathered together, compressed into a glowing lens where distant galaxies, ancient suns, and eons of cosmic history stream down toward you in a steady, unbroken cascade of pale light. Ahead of you, there is only an absolute, pristine dark. Outside the horizon, space was an open landscape. You could move forward or backward, climb upward or descend, turn left or steer right. Space offered choices, while time moved in only one direction, carrying you quietly into the future, whether you wished it or not. Here, inside the event horizon, that fundamental geometry has undergone a complete, surreal reversal. The spatial path leading inward toward the center is no longer a direction you can choose to travel or avoid. The extreme curvature of space-time has folded the radial dimension into time itself. Moving inward is no longer a physical journey through space. It has become your temporal future. To understand how strange this is, think of your own life on Earth. You can stand still in your room, but you cannot stand still in time. You cannot choose to stop moving toward tomorrow. Next hour, next day, and next year will arrive regardless of where you step or what direction you face. Inside the event horizon, the central core of the black hole is no longer a place sitting somewhere ahead of you on a map. It is a moment in time waiting in your inevitable future. Trying to fire engines to move backward toward the horizon would be like trying to build a machine to travel back to last Tuesday. It is not a matter of having enough fuel or powerful engines. The very fabric of space-time has turned every path, every beam of light, and every possible trajectory inward, all forward-directed light cones. The mathematical boundaries that determine where any particle can travel are tilted entirely toward the center. Yet, floating here in the quiet dark, there is no sense of chaotic motion. You are in free fall along a smooth geodesic path, weightless and calm. This is the region where classical physics reaches its limits and begins to whisper its deepest uncertainties. According to Albert Einstein's theory of general relativity, your journey inward follows a smooth, continuous path toward a central point of zero volume and infinite density, the singularity. In classical mathematics, every path ends there, crushed down into a spatial point where the curvature of space-time becomes infinite. For decades, textbook physics presented this singularity as a physical destination, a microscopic point where all the mass of a collapsed star resides. Modern theoretical physicists look at that prediction with deep skepticism. When a physical theory produces a result of infinity, whether it is infinite density, infinite temperature, or infinite curvature, it is rarely a description of the real world. Instead, it is a signal that the theory itself has reached the edge of its validity. It is a place where general relativity is crying out for help, warning us that it cannot solve the puzzle alone. To describe what truly happens near the center, we need a theory that combines gravity with the quantum world, the rules that govern subatomic particles. Some physicists hypothesize that quantum effects might create a repulsive force at microscopic scales, preventing matter from ever collapsing down to a true zero-point singularity. Instead of an infinite point, there might exist a dense, vibrating core of quantum foam, a Planck star, or a fundamental structure woven from the threads of space-time itself. Others suggest that the smooth continuum of space and time breaks down entirely at these extreme scales, dissolving into a chaotic network of quantum probabilities where the concepts of before and after, inward and outward, lose all meaning. You float peacefully in this realm of quiet uncertainty. Above you, the circular window looking back at the outer cosmos grows smaller and brighter, a lonely diamond of starlight shining down through the dark. In front of you, the unknown future waits quietly, wrapped in the mysterious mechanics of a universe still waiting to be fully understood. Take a slow, deep breath. The greatest mystery. Imagine holding a book in your hands. It could be an old, leather-bound volume filled with centuries of history, poetry, and human thought. Every word printed on its pages is composed of ink molecules arranged in precise patterns. Every page has a distinct texture, weight, and history. Now, imagine throwing that book into a roaring fireplace. As the fire burns, the paper turns to grey ash, smoke rises into the air, and heat radiates out into the room. To human eyes, the book is destroyed. The words are gone, lost forever in the flames. In the world of fundamental physics, however, that book was not destroyed at all. According to the unbreakable principles of quantum mechanics, the detailed information that described every atom, every particle, and every ink mark in that book is strictly conserved. If you had an impossibly powerful quantum supercomputer, and you were able to collect every single atom of ash, every particle of smoke, and every photon of heat released by the fire, you could theoretically reverse the equations and reconstruct every single word written on those burned pages. This is the principle of quantum determinism and the conservation of information. Information in our universe can be scrambled, hidden, or transformed, but it can never be truly erased from existence. The past is always preserved in the quantum state of the present. That fundamental law held true for centuries, until physicists began looking closely at black holes. In the early 1970s, a young Israeli-Mexican physicist named Jacob Bekenstein made a startling proposal. He suggested that black holes are not completely featureless voids, but that they possess real thermodynamic entropy, a measure of internal disorder and hidden information. Bekenstein argued that the area of a black hole's event horizon is a direct measure of its total entropy. When matter falls into a black hole, the event horizon grows slightly larger, taking in the entropy of whatever was consumed. At first, many theoretical physicists were skeptical, including Stephen Hawking. Hawking set out to prove Bekenstein wrong mathematically. He reasoned that if a black hole had entropy and a temperature, it would be forced to emit thermal radiation, which seemed impossible for an object from which nothing could escape. Using the tools of quantum field theory and curved space-time, Hawking performed the calculations and discovered, to his own astonishment, that Bekenstein was correct. Hawking showed that near the event horizon, quantum fluctuations constantly produce pairs of virtual particles out of the empty vacuum. Normally, these particle pairs collide and annihilate each other almost instantly. But near the boundary of a black hole, one particle can fall past the event horizon into the dark, while the other particle escapes outward into space as real thermal radiation. This faint glow of escaping energy is what we now call Hawking radiation. Because the escaping particle carries away a tiny fraction of energy, the black hole loses mass. Over unimaginably long spans of time, trillions upon trillions of years. A black hole will slowly lose its mass, shrinking millimeter by millimeter, until it eventually evaporates entirely in a final, quiet burst of light. And here lies the paradox that shook the very foundations of physics. If you throw that same book into a black hole, the book crosses the event horizon and is sealed away. Trillions of years later, the black hole completely evaporates, leaving behind nothing but a featureless cloud of Hawking radiation. That radiation is completely random and thermal. It carries no memory of whether the black hole consumed a book, a mountain, a star, or a galaxy. If the black hole completely vanishes, and the radiation left behind is purely random, where did the information go? If the information was permanently erased from the universe, then the fundamental connection between cause and effect breaks down. Quantum mechanics crumbles. The past no longer dictates the present, and the future cannot be predicted from the past. This is the black hole information paradox, one of the most famous conflicts in the history of science. It set two of the greatest pillars of modern physics, general relativity and quantum mechanics, in direct opposition to one another. For decades, theoretical physicists engaged in what became known as the black hole war, debating whether information was lost forever or somehow preserved. In recent years, brilliant new concepts have emerged to address this profound mystery. One leading idea is the holographic principle, developed by Gerard 't Hooft and Leonard Susskind, and expanded by Juan Maldacena. It suggests that all the three-dimensional information of everything that falls into a black hole is encoded as a subtle quantum pattern on the two-dimensional surface of its event horizon, much like a 3D image stored on a flat hologram. As the black hole evaporates, the escaping Hawking radiation subtly interacts with this surface pattern, carrying the encoded information back out into the universe in an incredibly scrambled but non-random form. Information, it seems, may be saved after all. The universe holds tight to its secrets, preserving the past even in the deepest shadows of gravity. Floating here in the quiet expanse of the inner horizon, looking back at the tiny point of starlight above, these daunting intellectual battles feel strangely peaceful. They remind us that black holes are not merely destructive monsters. They are nature's ultimate laboratories, cosmic mirrors that reveal where our human understanding ends, guiding us toward the next great revolution in physics. Take a slow, deep breath. Could you escape? Inside the event horizon, a quiet, persistent thought naturally takes root. Is there any way back out? It is an instinct deeply woven into the human spirit. Whenever we are confronted with a closed door, an absolute boundary, or a path from which there appears to be no return, our minds instinctively search for a loophole. We look for a flaw in the equations, an undiscovered property of matter, a secret tear in the fabric of space-time, or a hidden emergency exit that might allow a traveler to turn around and step back into the familiar, starlit world left behind. For more than a century, theoretical physicists have probed the mathematical limits of Albert Einstein's theory of general relativity to test whether the geometry of space-time leaves any such passage open. When you allow the equations to run to their absolute mathematical extremes, space-time yields some of the most extraordinary theoretical structures ever conceived. The first of these mathematical concepts is the white hole. In the elegant, pristine geometry of general relativity, the fundamental laws of motion do not distinguish between time moving forward and time running in reverse. If you take the classic mathematical solution for a simple, static black hole and extend the field equations backward through time, a remarkable mathematical mirror image appears, where a black hole is defined as a region of space where nothing can ever escape and everything must move relentlessly inward. A white hole is its exact inverse. It is a theoretical region of space into which nothing from the outside universe can ever enter, and from which matter, light, and high-energy radiation are continuously pushed outward into space. An event horizon still exists around a white hole, but its directional arrows are reversed. Light can shine outward from its boundary, illuminating the cosmos. But no physical object from the outside universe can ever cross inward through its threshold. When theoretical physicists examined what happens if you mathematically join the interior of a black hole to the interior of a white hole, the geometry produces a continuous, narrow channel through the fabric of space-time. An Einstein-Rosen bridge, known more popularly as a wormhole. On paper, an Einstein-Rosen bridge looks like the ultimate cosmic shortcut. It presents the breathtaking image of a theoretical tunnel connecting two vastly separated points in the universe. Entering a black hole in one corner of our galaxy could, in principle, carry a traveler through the bridge to emerge from a white hole in a distant galaxy millions of light years away, or perhaps even in an entirely separate parallel universe. For generations, this concept has captivated writers and dreamers alike. It offers a vision of space travel that bypasses the strict cosmic speed limit of light, turning the most dangerous objects in the universe into doorways through space and time. Yet, as physicists move beyond pure geometric idealizations and began examining the actual physical environment of our cosmos, those paper doorways quickly dissolved. A simple, unassisted wormhole is fundamentally non-traversable. The moment any real particle carrying mass or energy attempts to enter the passage, its own gravitational presence destabilizes the delicate balance of the bridge. The walls of the tunnel react instantly, causing the throat of the wormhole to pinch off and collapse in a tiny fraction of a second. The bridge snaps shut long before anything. Even a single photon of light could ever reach the opposite side, leaving behind only a central singularity. To hold a wormhole open and allow safe passage through its throat, you would need something extraordinary, a substance possessing negative mass and negative energy density. In classical mechanics, all known matter has positive mass. It pulls on space-time through attraction. Negative energy, if it existed on a macro scale, would exert a repulsive gravitational force, acting as a structural brace against the collapsing walls of space-time. While microscopic, transient negative energy fluctuations can occur briefly at quantum scales due to subatomic phenomena like the Casimir effect, there is no evidence anywhere in our universe that macroscopic quantities of exotic negative matter exist. Without exotic matter to prop the doorway open, a wormhole remains a fascinating artifact of blackboard mathematics, rather than a real destination in the sky. Furthermore, white holes themselves face insurmountable physical objections. Unlike black holes, which form naturally and routinely from the gravitational collapse of real dying stars, there is no physical mechanism in our universe capable of creating a white hole. Creating one would require a local decrease in entropy over vast regions of space, directly violating the second law of thermodynamics. If theoretical shortcuts through space-time offer no exit, what about raw physical force? Could powerful rockets, advanced propulsion systems, or immense energy reserves push you backward against the dark? Here, we encounter the deepest and most profound truth of black hole physics. The barrier to escape is not a technological limitation, nor is it a matter of engine power. It is a fundamental property of how space and time are constructed once you step past the threshold. Outside the event horizon, space provides you with three familiar spatial dimensions. You have complete freedom of direction. You can move up or down, step left or right, or walk forward and backward. If you enter a room, you can stand still, turn around, and walk out the door you came through. Space offers choices. Time, on the other hand, is the single dimension that flows in only one direction, carrying you relentlessly from yesterday into tomorrow without your consent. Inside the event horizon, those geometric roles undergo a complete and total swap. The spatial path leading inward toward the central singularity now behaves like time. Moving inward along the radial coordinate is no longer a spatial direction you can navigate or avoid. It has become your temporal future. To understand why mechanical thrust cannot help you escape, imagine standing in your room on Earth and trying to build a rocket that can take you back to yesterday. No matter how much fuel you burn, no matter how powerful your engines are, every tick of your clock carries you forward into tomorrow. Inside a black hole, trying to fire an engine outward toward the horizon is mathematically identical to trying to drive a spaceship into the past. The fuel you burn does not push you outward in space. It simply accelerates your consumption of proper time, bringing you to the central future moment faster than if you had simply floated weightlessly. The absence of an escape route is not a failure of engineering, imagination, or human technology. It is a geometric reality. Floating here in the quiet dark, accepting this truth brings a profound sense of peace. The frantic search for a back door falls away. There is no panic, no urgent calculation, and no struggle against the fabric of reality. You are simply a weightless observer, carried along the natural, unforced geodesics of curved space-time. The sky above remains open to your gaze, holding its luminous portal against the dark as you move onward into the unknown. What would the universe look like? Looking back toward the boundary you crossed, the outside world has transformed into an extraordinary visual display. The wide, open canopy of stars that once filled your sky from horizon to horizon is gone. Instead, the extreme curvature of space-time has gathered the incoming light from the rest of the cosmos, squeezing the outside universe into a bright, luminous circular window directly above you. Everything that has ever happened in the outer universe, every beam of light emitted by distant suns, and every photon that happens to fall into the black hole after you, is converging into this single visual portal set against absolute night. As photons from the outer cosmos fall down the steep gravitational slope toward your position, they gain energy along their path. This influx of energy creates a dramatic shift in how that light appears to your eyes. Wavelengths of light arriving from deep space are shifted upward in frequency, a process known as gravitational blue shift. Longer, warmer wavelengths of light transition into cooler, brighter colors. Deep red nebulae shift into warm gold and emerald green. Yellow suns brighten into brilliant cyan, and much of the visible light drifts up toward intense indigo and invisible ultraviolet bands. The circular portal above looks like a glowing blue eye set into a vault of pure obsidian, framed by a delicate, pale halo of starlight. Because incoming light rays approaching from extreme angles are bent sharply around the black hole's geometry, the rim of this circular window mirrors the outer sky in thin, recursive rings of starlight. The entire outside cosmos is repeated in fine, nested bands around the perimeter of the portal, wrapping the display in shimmering layers of optical reflection. Yet, despite popular pop science claims, you do not watch the entire infinite future of the cosmos play out before your eyes in a brief, instantaneous flash. What you actually observe depends on your exact trajectory, the specific mass of the black hole, and the finite duration of your personal descent. You do not witness the infinite end of time, rather, the incoming starlight simply arrives compressed in time relative to your local clock. Distant cosmic events send their photons down to you in accelerated bursts, casting a continuously changing, brilliant light across your field of view. Around your body, there is no blowing air, no physical dust, and no hard surface to reflect the beam. The incoming starlight streams straight through the dark void, illuminating nothing until it enters your eyes. You are suspended in a column of gathered starlight, watching the outer cosmos hold its steady position above. Consider the profound isolation of this vantage point. You are looking back at a universe that can still send you its light, its news, and its history. Yet you can send nothing back in return. You are a silent witness to the cosmos, receiving its final, beautiful signals as your journey draws toward its end. For a long while, you simply float and observe. There is no sound in the void. There is no sensation of falling fast, no rushing wind, and no physical pressure against your body. Weightless and calm, you watch the luminous blue window of the cosmos perform its silent, radiant dance in the dark sky above. You are seeing the universe from a perspective that no earthbound observer could ever experience. You are watching the history of space and time gather into a single portal of light, sharing a quiet moment of connection with the cosmos that continues its vast, ancient journey far above. The glowing window holds its steady light above you, shrinking slightly and growing more intense against the dark background as you glide further along your path. The universe above is aging, transforming, and sending its final beams of light down to keep you company in the quiet dark. Take a slow, deep breath. Do black holes die? As you hang suspended within the deep curvature of space-time, watching the outer world recede into a quiet circle of distant light, a fundamental question takes shape. Is this shadow permanent? Will the black hole around you remain forever? An unyielding vault standing sentinel long after every star in the cosmos has burned out its fuel. For decades, the classical physics formulated by Albert Einstein suggested a stark, eternal answer. In classical general relativity, a black hole is a one-way bridge in space-time that only ever grows. It absorbs passing gas, swallows colliding stars, merges with neighboring masses, and holds whatever crosses its threshold in an absolute, unbreakable grip. In that picture, a black hole is an immortal monument, a final, unchanging resting place for matter and energy, doomed to persist endlessly against the slow, cold, expanding background of space. Yet when we look deeper, marrying the smooth geometry of gravity with the subatomic mechanics of the quantum realm, a subtle and revolutionary truth emerges. Black holes are not permanent. They are patient, but they are not immortal. Over vast, unimaginable stretches of time, every black hole in the universe is slowly, imperceptibly decaying. To understand how a giant made of compressed mass and warped geometry can vanish, we must re-examine the nature of space itself. In everyday experience, we think of a vacuum as empty nothingness, a void completely devoid of matter, heat, or activity. But in quantum field theory, there is no such thing as absolute emptiness. The vacuum of space is alive with activity. It is a quiet, continuous ocean of subatomic field fluctuations, where pairs of virtual particles and their corresponding antiparticles constantly pop into existence out of empty space, exist for a tiny fraction of a microsecond, and then collide and annihilate each other, returning their energy back to the vacuum. Under ordinary conditions in deep space, this perpetual creation and destruction balances out perfectly. The energy borrowed from the vacuum is instantly paid back, leaving the overall state of empty space unchanged. However, near the boundary of an event horizon, the extreme curvature of space-time disrupts this delicate balance. When a virtual particle pair materializes right at the edge of the horizon, the steep gravitational gradient can separate the two partners before they have a chance to meet and annihilate. One particle drops past the invisible threshold, falling into the interior of the black hole. The partner particle, stranded outside the horizon, is left without an antiparticle to annihilate with. Unable to return to the vacuum, it is launched outward into open space as a real, physical photon of thermal energy. This faint, microscopic leakage of radiation is what theoretical physics calls Hawking radiation, named after Stephen Hawking, who mathematically derived its existence in the mid-1970s. Because energy in the universe must always be conserved, the particle that escapes outward into space carries real energy away with it. That energy must come from somewhere. The particle that fell past the horizon into the dark effectively carries negative energy relative to the outside world, subtracting a minuscule portion of mass from the central black hole. Every time a photon escapes into the night sky, the black hole loses a tiny fraction of its total weight. From your position inside the horizon, this decay does not appear as a violent storm. It is an extraordinary, slow process of cosmic evaporation. The rate at which a black hole leaks its mass into space is inversely proportional to its size. Counterintuitively, the larger a black hole is, the colder it is, and the slower it radiates its energy. For a stellar mass black hole, the remnant of a collapsed blue giant like the one we have been observing, the temperature of its Hawking radiation is far colder than the temperature of deep space itself. Right now, in the current era of our universe, the cosmic microwave background, the faint leftover heat from the Big Bang is warmer than the black hole's horizon. As a result, stellar black holes today absorb more energy from the surrounding background radiation than they emit through Hawking radiation. They are currently gaining weight, not losing it, only in the far distant future. After the universe has expanded for eons, stretching and cooling the background radiation to near absolute zero, will the balance tip. Only then will black holes begin their long, uninterrupted phase of physical evaporation. The timescales required for a black hole to completely radiate away its mass defy ordinary human metrics. A typical stellar mass black hole will take roughly 10 to the 67th power years to evaporate completely. A number represented by a 1 followed by 67 zeros. The supermassive monsters resting at the hearts of distant galaxies, containing billions of times the mass of our Sun, will endure for 10 to the 100th power years. To put those numbers into perspective, our entire universe is currently only about 14 billion years old. The era of stars, the brief period of cosmic history where suns ignite, planets form, and biological life thrives, is merely a short, fleeting morning at the very beginning of the universe's timeline. If you could remain suspended here in your local present moment, while eons rolled past in the outer universe, you would witness the grand, silent twilight of the cosmos. One by one, the stars in the night sky will burn through their remaining reserves of hydrogen and helium. White dwarfs will slowly cool into cold iron embers. Glowing nebulae will disperse into faint cold clouds of stray hydrogen. Galaxies will cease their bright spiral rotations, their light fading into a deep, unbroken shadow. The universe will enter what astrophysicists call the black hole era. It will be a cold, dark cosmos where stars no longer shine, and where black holes are the primary astronomical structures remaining in existence, acting as the final anchors of gravity scattered across the vast emptiness. Yet even those dark titans will not endure forever. As a black hole slowly loses mass over eons, its surface area shrinks, and as its mass decreases, its temperature begins to climb. A black hole with the mass of a planet would radiate at room temperature. A black hole with the mass of a mountain would glow with a hot, white light. During its final years, the evaporation process accelerates dramatically. The smaller the black hole gets, the hotter it glows, and the faster it sheds its remaining mass into space. In the final microsecond of its multi-trillion-year lifespan, the last remaining mass of the black hole vanishes in a quiet, brilliant flash of high-energy gamma rays. A clean, energetic release, marking the absolute end of a structure that once held stars in its orbit. When that final flash fades, the shadow is completely gone. The steep curvature of space-time that once defined the horizon relaxes back into a flat, calm state. The mass that was squeezed into extreme density is returned to the universe, transformed into a featureless, cold fog of radiation drifting endlessly through empty space. Floating inside the shadow tonight, you are experiencing an object that bridges the violent birth of massive stars to the ultimate, silent conclusion of cosmic time. You are suspended inside an entity that outlasts light itself, yet remains bound to the quiet, inevitable laws of change. As the light from the outside sky holds its steady position above, carrying its quiet signals into the dark, we prepare to leave the physical timeline behind, turning our attention to the final, lingering puzzle of our journey in Chapter 14, the last question. The last question. We have traveled across an extraordinary expanse of space and time. We began our journey floating safely in deep space, watching a quiet spherical shadow distort the distant stars. We moved forward past the glowing arcs of gravitational lensing, drifted through the orbiting light of the photon sphere, and crossed the invisible threshold of the event horizon without feeling a single thud or jolt. We watched space and time swap their conceptual roles, observed the strange warping of geometry, and looked ahead to the ultimate quiet evaporation of black holes in the far future of the cosmos. Yet, as our long journey draws to its final rest, we discover a profound truth about what we have been exploring. A black hole is not merely an extreme destination in space. It is a mirror held up to the absolute boundary of human knowledge. In the history of science, the most important breakthroughs have rarely come from places where our theories work smoothly. They come from the boundaries, the places where our mathematics breaks down, where our predictions produce absurdities, and where nature forces us to admit that our picture of reality is incomplete. The black hole is the ultimate boundary in all of physics. It sits precisely at the point of collision between the two great pillars of modern science, Albert Einstein's theory of general relativity and quantum mechanics. General relativity is our theory of the very large. It describes space-time as a smooth, continuous, flexible fabric that curves in the presence of mass, guiding the motion of planets, stars, and galaxies. It is deterministic, geometric, and elegant. Quantum mechanics is our theory of the very small. It describes the subatomic world not as a smooth fabric, but as a granular, jittery realm of discrete energy packets, subatomic field interactions, and fundamental probabilities. For over a century, both theories have proven astonishingly accurate within their own domains. General relativity correctly predicts the motion of binary pulsars and the bending of starlight. Quantum mechanics correctly explains the behavior of atoms, the light of lasers, and the microchips that power human technology. Yet, at the center of a black hole, these two foundational theories are forced into the exact same room, and they flatly contradict each other. General relativity, treating space-time as a smooth continuum, predicts that the core of a black hole must collapse into a singularity, a point of zero volume, infinite density, and infinite space-time curvature. Quantum mechanics rejects that conclusion. It states that space itself cannot be infinitely smooth, that physical energy comes in indivisible minimum units, and that fundamental quantum information can never be completely compressed out of existence or destroyed. When our mathematical equations produce an answer of infinity, it is not nature telling us that infinity physically exists in a room. It is nature telling us that our equations have run out of answers. The singularity is not a physical object resting in space. It is a signpost marking the exact edge where human physics currently breaks down. This contradiction is not a failure of science. It is an invitation. It tells us that our current concepts of space, time, and gravity, as fundamental and real as they feel to our everyday senses, are likely not fundamental at all. Just as a smooth ocean wave is actually made of trillions of discrete water molecules, the smooth space-time described by Einstein may simply be a large-scale approximation, a surface illusion emerging from a deeper, underlying network of quantum information. Theoretical physicists around the world spend their lives working at this frontier. They build new mathematical languages, like loop quantum gravity, string theory, and holographic physics, searching for the single, underlying framework of quantum gravity that can merge the smooth curve with the subatomic particle. They are searching for the language that describes what happens when space itself is broken down into its smallest possible threads. Yet as you float here in the weightless dark, looking up one last time at the tiny, distant portal of starlight above, a quiet perspective settles over the mind. We often grow up believing that science is a process of closing doors, a method of systematically taking the wonder out of the world, replacing mystery with cold facts, rigid labels, and settled formulas. The black hole proves the exact opposite. The deeper we push our telescopes into the night sky, and the more rigorously we calculate the geometry of space-time, the more the universe reveals its infinite depth. Black holes demonstrate that reality is vastly richer, stranger, and more subtle than our local, everyday senses were built to comprehend. They remind us that we live in a universe that still holds profound, unwritten chapters waiting to be discovered. Look back at that faint circle of starlight hanging in the dark sky above. You have journeyed through a realm where light curves into loops, where the radial path forward behaves like time itself, where stars leave behind silent gravitational ghosts, and where the far future of the cosmos plays out in long, unhurried eons. If the very fabric of space and time can stretch, swap roles, and fade away at the edge of a shadow, what else about our reality have we mistaken for absolute certainty? What if our experience of time flowing forward, our perception of distance, and our belief in solid surfaces are merely gentle approximations, useful tools for daily life, but only a tiny fraction of a far grander picture? The universe offers no quick answer to that question. It does not speak in words or equations. It simply rests in its ancient, patient stillness, holding its deep mechanics in the dark, waiting for human curiosity to take its next step forward. The starlight above is calm. The void around you is weightless and still. The equations fade away into the quiet expanse of space, and the question lingers softly in the dark as you drift peacefully into sleep.